Welcome to AI Unraveled, your daily briefing on the real-world business impact of AI. If you are a CTO, your single biggest concern isn't performance, it's trust. How can you deploy AI that is secure and compliant when the real-world data feeding it is inherently biased and full of privacy risk? You can't trust the data, so you can't trust the model. That changes today. In this special episode, we introduce the synthetic data supply chain, a fundamental framework for zero-trust AI. This is a massive shift, arguing that model security starts and ends with verifiable data integrity. We're breaking down the architecture, the four governance pillars, provenance, quality assurance, lifecycle, and access control, and demonstrating how synthetic data proactively mitigates systemic bias and achieves provable privacy via differential privacy. This is essential, non-negotiable knowledge for anyone deploying AI at scale. But first, a quick word for the enterprise builders. Stop marketing to the general public, talk to enterprise AI builders. Your platform solves the hardest challenge in tech, getting secure, compliant AI into production at scale. But are you reaching the right 1%? AI Unraveled is the single destination for senior enterprise leaders, CTOs, VPs of engineering, and MLOps heads who need production-ready solutions like yours. They tune in for deep, uncompromised technical insight. We have reserved a limited number of mid-roll ad spots for companies focused on high-stakes governed AI infrastructure. This is not spray and pray advertising. It is a direct line to your most valuable buyers. Don't wait for your competition to claim the remaining airtime. Secure your mid-roll spot here. Link in show notes. Let's unravel the zero-trust framework for ethical AI.
Welcome to the deep dive. Today we're jumping right into something critical, maybe the most fundamental vulnerability in, modern AI. We spend so much time talking about the latest models, huge parameter counts, faster algorithms. But the real weak link, the thing that decides if an AI is actually secure or private or fair, it's the data, the stuff used to train the model from day one. I mean, think about it. Your standard real-world data, it's inherently risky. It's just a minefield of potential privacy violations, it's packed with systemic biases, and maybe most crucially for anyone building something important, it's often scarce. You can't kick off a major drug discovery program if the crucial data on rare conditions is just, locked up somewhere. So the answer isn't simply making more data. It's about applying some serious industrial-level rigor to how we make it. We're talking about the synthetic data supply chain. Think of it as a structured, governed, really end-to-end process for creating high-quality, artificial data. Data that mirrors statistical reality, but crucially, without carrying all that real-world baggage and risk.
Exactly. And our mission today really is to show you why this supply chain is. Well, it's the essential foundation for what we're calling zero-trust AI. This isn't just about making things run smoother or faster. It's a fundamental shift in where we draw the security perimeter.
Okay. So zero trust. I usually hear that in terms of networks.
Right. And for networks, it's that simple, powerful idea: never trust, always verify. What we're doing is extending that same mandate to the data itself. If you can't verify that the data going in is secure and private and fair, then you simply cannot trust what the model spits out. The data pipeline itself, that's the new frontier we absolutely have to secure.
Yeah, to really get this shift, just think back to the basics of zero trust architecture for networks. It was a move away from that old model, the castle and moat.
Where if you were inside the walls, you were trusted. Exactly, and that just doesn't cut it anymore. Zero trust demands constant verification. It rests on three core ideas. First, verify explicitly. Always authenticate based on identity, location, device health, you name it. Second, use least privileged access. Give people only the access they need for only as long as they need it. Just in time, just enough access. And third, maybe the most important mindset shift: assume breach. Design everything, assuming the bad guys are already inside.
Or, in our case, assuming they're already messing with the data.
Precisely. And that's where applying this to AI data gets really, really critical. We all know that old saying, right? Bad data in, bad data out.
Sure, garbage in, garbage out.
But zero trust forces us to treat that input data as potentially the most dangerous attack vector we have.
You mean things like data poisoning, where someone sneaks bad examples into the training set?
Exactly. Adversarial attacks like data poisoning demonstrate it perfectly. An attacker compromises the pipeline, maybe injects just a tiny fraction of malicious inputs, and suddenly the entire model's integrity is shot. It becomes untrustworthy. The second you adopt that assume breach mentality, you have to admit, raw, real-world data is inherently an untrusted asset.
Okay, so What makes it so untrustworthy? You mentioned categories of risk.
Yeah, this inherent distrust really stems from three main types of risk. These make real data a huge liability for any serious organization. Risk number one, privacy risks. This is the obvious one. Real data is just littered with personally identifiable information, PII.
Names, addresses, social security numbers.
All of it. Using that data instantly creates massive regulatory headaches. Think GDPR, HIPAA. If you're training, say, a customer service bot on actual call transcripts, every single conversation is a potential lawsuit waiting to happen.
So you spend more time locking down the data than actually using it.
You got it. The risk of a leak, even an accidental one, is just too high for broad access. Okay, number two, bias risks. This one is maybe more insidious. Real data reflects our messy, often prejudiced history. So if you train a hiring algorithm on decades of data from a male-dominated industry, guess what?
It learns to prefer male candidates.
Exactly. The model isn't being malicious, it's just faithfully learning the biases embedded deep in the data. It's not learning objective reality, it's learning the historical record of reality, warts and all.
Right. That makes sense.
And finally, number three, scarcity and quality risks. This hits hard in critical areas. Think about cutting-edge financial fraud detection. Fraudsters constantly change tactics, so getting high-quality, correctly labeled examples of the newest fraud schemes, that's incredibly difficult. The data is just rare.
And if your training set is tiny?
It's highly vulnerable to being skewed or compromised. You just can't get the statistical reliability you need, and if you can't rely on the data, you definitely can't trust the AI built on it.
So real data is risky, biased, often scarce. That sounds like a terrible foundation. This supply chain idea, then, it's about building trust where there isn't any.
That's the core concept. It's a trust transference mechanism. The synthetic data supply chain is that formal, structured process designed specifically to take raw, inherently low-trust data and transform it into a high-trust asset through a series of verifiable, auditable stages.
Okay, let's walk through those. What are the stages?
It's essentially a 6-stage pipeline. Stage 1 is absolutely fundamental, source data analysis and cleaning. The quality of your synthetic output depends entirely on how well you understand the real data you start with. This is where you extract the data's identity card. It's statistical fingerprint, finding anomalies, understanding correlations, cleaning it up.
So garbage in, slightly less garbage out if you don't do this first step right.
Pretty much. Then, stage 2, objective definition and model selection. You have to be crystal clear about why you're making synthetic data. Is it to fix a known bias? Like, say, underrepresentation of women in loan application data? Or are you generating millions of fake transactions just to hammer a payment system and see if it breaks?
The why dictates the how.
Exactly. The objective determines which generative model you pick, maybe a GAN, maybe a VAE, maybe something else entirely. Stage 3 is control generation. This is where the magic happens, the actual creation. But it demands really meticulous documentation. You need to log everything. The specific models used, all the tuning parameters, the hyperparameters, even the random seeds that kicked off the generation. All this metadata establishes what we call data provenance.
Hold on, that sounds like a lot of work. Data provenance, logging every seed. For a small team trying to move fast, isn't that overkill? How do you justify that?
It might feel like overkill, but in a zero-trust world, it's absolutely the cost of doing business. It's the cost of trust. Think about it. If a regulator or your own internal audit team comes knocking and questions the validity or fairness of your synthetic data, what's your answer?
Oh.
Provenance is your audit trail. It guarantees reproducibility. It proves the data was made according to defined policies, not just whipped up arbitrarily or worse, maliciously tweaked. It's non-negotiable for trustworthy AI.
Okay, fair point. What's stage 4?
Stage 4 is critical for making sure the data is actually useful. Quality assurance and validation. This isn't just one check. It's got 3 key dimensions. First, statistical similarity. Does the synthetic data actually mirror the real data's distributions, its correlations? You need metrics for that. Second, bias and fairness audits. Did we accidentally introduce new biases, or did we successfully mitigate the ones we targeted? And third, something called workload-aware utility.
Workload-aware utility. Explain that one a bit more.
This is the real asset test. It's often called the train on synthetic, test on real evaluation, or TSTR. You take your AI model, you train it only on the synthetic data you just generated. Then you test its performance on a clean, held-back sample of the original real-world data.
So if it performs well on real data after only seeing synthetic.
Can you know your synthetic data captured the essential patterns, the intelligence needed for that specific task? It proves utility.
Makes sense. What are the last two stages?
Stage 5 is integration and deployment. The validated synthetic data gets fed into your MLOps pipelines, your machine learning workflows. But crucially, it must always be clearly labeled as synthetic. No mixing undetected. And finally, stage 6, lifecycle management and iteration. Data gets stale. The real world changes. So you need version control for your synthetic data sets and clear policies for when to retire old versions. You have to prevent people from using zombie data sets that no longer reflect reality.
I guess automation is key to making all this scale, right?
Yeah.
Applying that MLOps discipline to the data creation itself.
Absolutely. That gets you towards what some people call continuous integration, continuous generation, or CICG. Automated testing, automated validation, continuous monitoring for things like data drift. That's when your synthetic data starts to diverge from the changing reality it's supposed to model. Automation makes this manageable.
Okay, let's dive into the engine room then.
Yeah.
Stage 3 mentioned model selection. What are the main workhorses here? The algorithms doing the heavy lifting. I hear a lot about GANs and VAEs, generative adversarial networks and variational autoencoders. What are the key trade-offs?
Yeah, those are definitely two of the dominant approaches, though new ones are emerging too. The fundamental difference is really in how they generate realistic data. GANs are probably more famous, known for generating really high-fidelity, sharp outputs, especially for images or video.
That's the one with the two networks fighting each other, right? The generator and the discriminator.
Exactly. You have a generator creating fake data and a discriminator trying to tell the fakes from the real examples. This constant competition, this adversarial game, forces the generator to get incredibly good at mimicking reality. But, and it's a big but, GANs are notoriously tricky to train. They can be very unstable.
Unstable how?
Their biggest failure mode is something called mode collapse. It's a serious problem.
Okay, walk us through mode collapse. Why is that so bad?
It's bad because it kills diversity, which is often the whole point of using synthetic data. Imagine your real data set has, say, 10 distinct types of customer behavior. During training, the GANs generator might figure out it can reliably fool the discriminator by only producing, say, 2 of those 10 types. It just gets really good at those 2 modes.
So it stops bothering with the other 8.
Precisely. It collapses onto the modes where it finds success easily. The result, you get this synthetic data monoculture. You might look at the individual samples and they look great, really high quality, but you've actually failed to capture 80% of the true variety in your original data.
And the downstream model trained on that.
It'll perform brilliantly on the 2 modes it saw and then fall flat on its face when it encounters any of the other 8 in the real world. Catastrophic failure waiting to happen.
Ouch. Okay, so what about VAEs? Are they the safer option then?
They're generally considered the more stable, calmer alternative. VAEs work differently. They use an encoder-decoder architecture. The goal is explicitly to learn the underlying probability distribution of the data. Map the data to a compressed latent space and then decode it back. This process is inherently more stable, much less prone to mode collapse. They tend to give you good coverage of the data's distribution.
Okay, stability sounds good. What's the downside?
The trade-off is often in the output quality, the realism. VAE outputs can sometimes look a bit blurrier or smoother, less sharp than the best GR results. But their big advantage, besides stability, is often better controllability. Because they learn that structured latent space, you can often manipulate points in that space to more predictably control the features of the data you generate. It's more interpretable.
And what about newer things? Like diffusion models, the things behind stable diffusion and Midjourney.
Right. Diffusion models are definitely the state of the art now for image generation quality. They produce stunningly realistic results, but they currently come with a significantly higher computational cost. They take longer to train and longer to generate samples compared to most GANs and VAEs, so it's another trade-off.
So it sounds like there's no single best engine.
Not at all. A mature synthetic data supply chain won't rely on just one technique. It'll use a portfolio. Maybe use GANs when you absolutely need that photorealistic sharpness. Use VAEs when stability, distribution coverage, and control are paramount. Maybe explore diffusion models for specific high-fidelity tasks if you have the compute budget. It's about matching the tool to the specific job defined back in stage 2.
Okay, so we've engineered for security through provenance. We've engineered for utility through validation like TSTR. But we still need to tackle the really core ethical challenges, making sure this AI isn't just effective, but also fair and private. Does synthetic data help there?
It absolutely does. In fact, it offers powerful ways to proactively engineer fairness and privacy, rather than just trying to patch problems after the fact.
How do you engineer fairness?
Mhm.
Bias comes from the real data, right?
It does, but synthetic data lets us actively counteract that bias through techniques like targeted oversampling. We already said algorithmic bias often stems from flawed data. If your real data set has very few examples of a certain group, maybe a specific demographic in loan applications, or patients with a rare disease, the model won't learn to handle that group well. It leads to unfair outcomes.
So oversampling means making more examples of that minority group.
Exactly. With targeted oversampling, you use your generative engine, maybe a VAE, because of its controllability, to specifically create new, realistic synthetic examples only for that underrepresented group. You carefully add these synthetic samples to balance the data set. You're essentially giving the model a more equitable version of history to learn from.
That's a big shift. It's not just cleaning the data, it's actively reshaping it for fairness.
It's a fundamental ethical shift. We move from passively asking, gosh, is our data biased, to proactively defining and building towards the question, what does a truly fair data set actually look like for this problem? We engineer it.
Okay, that's powerful for fairness.
Mhm.
What about privacy? You mentioned the PII landmine earlier. Simple anonymization, just scrubbing names, isn't enough.
It really isn't. Simple anonymization is notoriously brittle. Attackers can perform re-identification attacks. They link those supposedly anonymous records with other public datasets using quasi-identifiers, things like zip code, date of birth, maybe job title. Put enough of those together, and you can often pinpoint individuals.
So we need something stronger, a real guarantee.
We do. And the gold standard for that mathematical guarantee is differential privacy, or DP. DP isn't an algorithm itself, it's more like a mathematical promise, a property of an algorithm. It provides a formal guarantee that the output of the algorithm, in our case, the synthetic data, is statistically almost identical, whether or not any single individual's data was included in the original input dataset.
How does that work? How can you make that guarantee?
You achieve it by carefully injecting a controlled amount of random noise during the generation process. Think of it like adding static to a phone line. We control the amount of privacy using a parameter, usually called epsilon, the privacy budget. It acts like a lever or maybe a dimmer switch.
Okay, a dimmer switch for privacy.
Yeah. If you turn the privacy way up a small epsilon value, you add more noise. This makes it extremely hard, mathematically provably hard, to infer anything about any specific individual. Stronger privacy. But more noise means the data might become less accurate, less useful for training a high-performance model. The utility goes down.
There's the trade-off again.
Exactly.
Right.
If you turn the privacy down a larger epsilon, you add less noise. The data retains more of its original detail, higher utility. But you have a weaker mathematical privacy guarantee.
So choosing that epsilon value, that sounds like a really critical decision. You're directly balancing privacy risk against model performance.
It's a very deliberate strategic decision. There's no single right epsilon. It depends on the sensitivity of the data, the regulatory requirements, a specific use case. But the impact, especially in regulated fields like healthcare with IPA or finance, is huge. DP synthetic data becomes this incredible tool. It allows organizations to potentially share sensitive data insights, maybe for research collaboration or building new products, while having a mathematical proof that they are protecting individual privacy and meeting compliance rules. It's a negotiation tool between utility and liability.
Okay, this all sounds incredibly promising. Building trust, engineering fairness, guaranteeing privacy. But let's be realistic. Synthetic data can't be a perfect solution, right? It's not a silver bullet. There must be downsides, pitfalls we need to watch out for.
Absolutely. It's crucial to understand the limitations. The most immediate one is what we can call the realism gap. Remember, synthetic data is always an approximation of reality, generated by a model. And models, even good ones, can struggle. They might fail to capture very subtle, complex, maybe nonlinear relationships that exist in the real data. And crucially, they often struggle with capturing the true nature of rare events, the outliers.
The long tail of the distribution.
Exactly. Think about it. The generative model learns the common patterns really well, but those weird, infrequent edge cases, maybe a novel type of cyber attack, a bizarre market fluctuation, the model might smooth over them or miss them entirely.
So the synthetic data looks good on average, but lacks the crucial extremes.
Right. It's like drawing a map that only shows the major highways but misses all the small country roads. You capture the general structure, but you miss the details where often the really interesting or dangerous stuff happens.
And if your model trains on that smooth data, it might look great in testing.
But then fail unexpectedly when it hits that real-world complexity or those rare events in production. This leads to what some call synthetic data debt.
Debt, meaning you pay the price later.
Precisely. You thought you saved time or reduced risk up front, but you pay later with model failures, emergency retraining, lost revenue, maybe even reputational damage. It's a deferred cost.
Okay, that's a risk with a single model.
Yeah.
But you also mentioned a bigger, more systemic risk.
Yeah.
Something about model collapse.
Yes, model collapse. This is the potentially scary long-term danger, especially if we become over-reliant on synthetic data in a feedback loop.
What kind of feedback loop?
Imagine AI models being trained primarily on synthetic data. Then, the outputs of those models are used, perhaps inadvertently, as input to train the next generation of models. Maybe synthetic text generated by one LLM gets scraped and used to train another LLM. If that happens repeatedly, generation after generation, models trained only on the outputs of previous models risk gradually forgetting the nuances, the diversity, the tails of the original real-world data distribution. With each iteration, the data could become slightly more simplified, more homogeneous, reflecting the biases or limitations of the generative models themselves rather than reality.
So the AI ecosystem starts
Yeah.
drifting away from reality.
That's the concern. It could converge on a narrow, potentially impoverished, maybe even nonsensical view of the world. Think of an AI image generator trained only on images produced by other AI image generators eventually. Its concept of cat might become completely detached from actual cats. It's a potential systemic risk of losing touch with the grounding of real-world complexity and diversity.
Wow. Okay, that really highlights a critical point then. Synthetic data is powerful, but it can't completely replace real data, can it?
Absolutely not. That original, high-quality, real-world data, that golden copy you started with back in stage one, remains absolutely essential. It has to be the anchor, the ground truth. You need to periodically validate your synthetic data and the models trained on it against fresh, real-world data to prevent that drift, to detect model collapse before it goes too far. Reality must remain the benchmark.
And one last pitfall. Just the human element, getting people to trust this synthetic stuff.
Definitely. There's a significant challenge in stakeholder skepticism and change management. The term synthetic data itself can unfortunately trigger suspicion. People hear synthetic and think fake or inferior.
So you need to actively combat that perception.
You do. It requires real transparency. You need to be able to clearly explain the rigorous 6-stage supply chain process. You need to show the metrics from stage 4, the statistical similarity checks, the bias audits, and especially the TSTR results that prove the data works for the intended task. Building trust in the process is key to building trust in the output. #outro.
So let's bring this all together. What's the big picture takeaway for you, the listener?
It seems the synthetic data supply chain isn't just a technical process. It's really a fundamental governance framework. It's about transforming AI data from being this huge source of risk and scarcity into potentially a foundation of verified trust, enhanced security, and even engineered ethical abundance, which sounds pretty essential for any AI system that actually matters, any mission-critical application.
That's the goal. And looking ahead, we're likely to see a couple of key trends. First, deeper convergence. Generative AI techniques will become even more tightly integrated with privacy-enhancing technologies like differential privacy. They'll be designed together from the start. And second, standardization. We're already seeing movement from bodies like ISO and NIST to develop formal standards around synthetic data generation, provenance, quality assessment, and fairness metrics that will help build broader trust and adoption.
Okay, convergence and standardization. Makes sense. But this whole discussion leaves us with a really critical question, maybe a provocative thought to end on. If this synthetic data supply chain becomes, as it seems it might, the primary way we train many of our most important AI models, and we know that over-reliance on purely synthetic data risks this model collapse phenomenon, this gradual forgetting of real-world nuance, then what governance mechanisms, what safeguards do we need to put in place right now? How do we ensure that enough new, diverse, genuinely real-world data continues to flow into the system, constantly refreshing our models and keeping them anchored in the actual truth?
How do we keep AI from dreaming itself into a corner?
Exactly. Securing that continuous link to reality. That might be the next critical boundary we need to define and protect.
That's it for today's deep dive. We hope you walked away with actionable insights for your enterprise strategy. Before you go, let me remind you of the unparalleled value of this platform. AI Unraveled delivers deep, uncompromised technical insight that keeps our audience, senior enterprise leaders, tuned in to the very last minute. That sustained attention is the best place for your ad. This is your opportunity for a direct line to your most valuable buyers, the CTOs, VPs of engineering, and MLOps heads who sign off on high-stakes infrastructure. Stop wasting budget on general marketing noise. Secure your high-impact premium ad campaign right here. Email us today to reserve your mid-roll package, info@djamgatech.com. Thank you for listening to AI Unraveled. We'll be back tomorrow with more.